welcome to all of you to the International Conference of an Artificial Intelligence and Machine Learning Applications. I am overwhelmed to welcome our today's keynote speakers for the conference. The key to growth is the introduction of higher dimensions of consciousness into our awareness. Now, I request Dr. D. Srividya, Professor, Department of Electrical and Electronics Engineering, K.S. Rangasamy College of Technology, to introduce our today's keynote speaker.
Good evening, everyone. It's my pleasure to introduce such an eminent person to our conference. Dr. Hermano Igo Krebs is a principal research scientist, lecturer at MIT Mechanical Engineering Department and director of 77 labs. He holds an affiliate position as an adjunct professor at University of Maryland School of Medicine, Department of Neurology. And he is a visiting professor in 3 universities, namely Fiji Health University, Department of Physical Medicine and Rehabilitation, Japan, and at ASCO University, Mechanical Science and Bioengineering Department, Japan, and at Loughborough University, Rehabilitation Robotics of Wolfson School of Mechanical and Electrical and Manufacturing Industry. He is a fellow of IEEE and was nominated to the Distinguished Engineering status for contributing to rehabilitation robotics and understanding of neurorehabilitation. He received 2 awards at the 2009 Isabella and Leonard H. Goldson Technology and Rehabilitation Award from Cerebral Palsy International Research Foundation. In 2015, IEEE INABA Technical Award for Innovation leading to produce for contribution to medical technology, innovation and translation into commercial application for rehabilitation robotics. He was selected as an 2021 IEEE ENDS Distinguished Lecturer. He was one of the founder, member of Board of Director and Chairman of the Board of Director of Interactional Motion Technology from 1998 to 2016. He successfully sold it to Bionic Laboratory, a publicly traded company, who served as a chief science officer and as a member of Board of Director until 2017. He later founded 4 Motion Robotics. Thank you, Professor, for delivering keynote address for our international conference.
No, thank you. Thank you so much for the opportunity. So let me share here my slides. And let me start here. Actually, I forgot to click on sound. So let me stop sharing and do this again because I didn't include the magic button to include computer sound. So now I did that. And let me try this again. And one more thing, let me see if I can see, back and the pointer. Okay, so thank you very much for this opportunity to present a little of our work. And what I'm going to be talking is, of course, it's the work of a team. I'm just one of the people in this team. So this is a teamwork. And I would start by trying to introduce you and present a little of what we do to give a kind of sense of the activities. And then discuss a little how we have been trying to develop biomarkers to estimate different characteristics of stroke recovery. So let me play first this video here.
Thanks for watching and stay with us. There's much more ahead on CNN, including today's edition of Pioneers. Take a look.
MIT scientists Hermano Igo Krebs and Neville Hogan are using robots to help stroke victims with brain injuries regain movement. Their arm robots have already helped patients move shoulders and wrists, enabling them to do things they couldn't do for themselves, like shower or put on clothes.
It isn't just a matter of moving. We are seeing something that looks like we're influencing a change in the brain. And I think that's probably the most important thing we've seen so far.
Now they're focusing on the lower extremities with ankle bots, which they hope will not only help patients walk again, but also help avoid dangerous falls after their strokes. The robots work by providing a video game on a screen, which prompts users to perform an exercise.
If they don't make that movement within a certain period of time, then the robot will initiate it. If they do make a movement within that period of time, the robot goes along and helps them. So what we think is happening is that the visual display evokes the intent to move. A short time later, movement actually happens, and that sensory information comes back up to the brain.
A future goal is to one day have an entire robotic gym for all parts of the body.
So what I'm going to talk a little today is about two of our recent papers that we got published right at the end of last year in the use of robotic kinematics to measure arm recovery in chronic stroke. This is the work primarily of this gentleman here, Caio Moretti. It was his PhD thesis. And let me start by trying to talk and go over different aspects. So rehab, like robots for rehabilitation, they promote better outcomes following stroke. We had shown that we can get better impairment reduction than when just limited ourselves to usual care therapy. And why is that? Is because we might think about these robotic devices as interfaces to computer games, and we enhance the patient attention and engagement, and we deliver much, much higher intensity of training. So in a typical therapy session, the therapist would engage the paretic limb maybe 40 or 45 times in a 45-minute session, while with this kind of technology, we engage the paretic limb 1,000 times in the same period. Now, we also can evaluate the outcomes because we are storing the movement and the behavior of the patient, so we can try to understand the different movement patterns. So this is what I'm trying to show here, where you would have the device, the robot, that is nothing more than an interface for training that normally use serious games, different forms of games that enhance the motivation of the patients, enhance the attention of the patients, and allow them to do much more intensive exercises. But at the same time, this device also, because of its actuators and sensors, allow us also to collect the data and later on try to analyze the data to try to find different patterns of the process of neural recovery and increase our knowledge. So we have started developing robots. Actually, when I was a student in 1998, I started developing the first robot that became known as the MIT Manus gym. It was a set of different robots to work with the shoulder and elbow. That was the first device. And again, we have actuators, but we also have sensors to measure the position, velocity, and the forces that the patient is interacting with the devices. And we can also change the way we control the robot. So we can also employ different forms of adaptive controllers that would help in different ways the patients to perform and improve their movement. But more importantly, these adaptive controllers also keep not only tracking the patient, but also keep challenging them to do more. Now, this was like, the robot for the shoulder and elbow, but we also develop robots to train the wrist or the hand. So not only we trained the proximal shoulder and elbow, but also the distal wrist and hand. And later on, we also develop robots for the lower extremity. But most of what I'm going to talk today is about upper extremity. So in particular, let me start introducing one of our first work that we published quite a few years ago, where we actually were looking to how patients were improving from admission and discharge, and using linear correlation to try to see if we could get better results. So this is, we use linear and also we use nonlinear. So let me talk a little about this nonlinear work. So this was work that we did for Johnson & Johnson. So Johnson & Johnson at the time was developing a potential drug for stroke recovery. So they wanted to compare and see if using robotics as an evaluation tool, we could get even better results than just using the clinical scales. So the typical way that you do studies in this kind of approach is that you start delivering the drug, say in day 7, and then you keep evaluating the patient at different days, day 14, day 21, day 30, day 90 after the stroke. So we did the same thing that normally they would do in any drug studies, but instead of just evaluating with the clinical scales, we also evaluated the patients using the robotic tool, the robots. We were not delivering any therapy for these patients. We were just using the robots as an evaluation tool. And the study enrolled 208 acute stroke patients. We actually enrolled them day 3 after the stroke. So right after the stroke, day 3, we engage them and start evaluating them starting at day 7, as it's done in different drug studies. So we did evaluate both the impaired and the unimpaired arm, and it became clear that when we were looking to the different correlations with the clinical scales using the linear scales, we saw that just using the affected side would be enough. So we didn't need to use the data that we collected on the unaffected side, because the combination of both the affected and the unaffected improve a little, but not much more. So it became much more practical in the future, because we want to do this. J&J, Johnson & Johnson wanted to do these studies in the future. They want to minimize the time to collect the data. So in this case, because the unaffected arm wasn't contributing that much, the goal would be then going forward only to use data collected with the affected arm. And at the same time, we have many different features, and we were looking how many features, depending on the clinical scale, how many features we should select in order to get a good approximation. So here you have a statistical embedded map. So these red dots represent the different clinical scales that typically are used by the clinicians. And then in blue, we have the affected arm, different metrics of movement that the patient are performing unassisted. And then in green, we have the unaffected arm. And this statistical embedded map, essentially what we are doing is that we are taking the correlation from each of the scales, say the Fugl-Meyer, with the deviation of the affected arm from the straight line when the people are making straight movements. We see what was the correlation, and we do 1 minus the correlation, and this we consider here to be the distance between the two. We then kind of stretch it to make it like a square, but trying to more or less preserve the distance. And then we can see which of the metrics are closest to the clinical scores. We then selected among these different clouds, we selected a few metrics, 8 metrics, to try to select which metrics we would move forward. We then use traditional ensemble of neural networks, where we were like essentially putting the different robotic metrics, and the outcome was the clinical scores. and we like try to see how well we could approximate them. Here is just like showing the different weights of the neural network. And here we start seeing a few interesting things. So first thing we did is that the study was with 208 patients. And then what we did is that we went to a data bank that is called Vista, and we selected patients that were matches. They match the patients that we had in our study. And we essentially got a 10 times fold increase on the match of the patients to have a look how those patients were changing with time using the clinical scores. And then we calculated the effect size using the robot biomarker or the clinical score. So here you have like the clinical score that we got from the historical data. And here, depending on the number of features, what was the effect size that we were getting using our nonlinear approximation. So we get a much, much better effect size when we use the robot biomarker, and it's somehow expected because we have a much better resolution than the clinical scales that were determined by the therapist. So when we look to the effect size, we have a significant reduction. So if we would be making a study for Johnson & Johnson to determine if the drug has an impact or not, we could reduce the number of patients by 70%. So to give you an idea, one drug that is commonly used after stroke is actually one of the few drugs that I had shown to have positive impact called TPA. The study that determined that the drug was positive enrolled 804 patients. If we had used the Robotic Metrics instead of the traditional clinical scales, with 240, we would have already determined that the TPA would have a positive impact. So this is like to tell you a little about the related work, things that we have done in the past, but we didn't do this in empty space. We had, of course, developed through the years a data structure where we save all the data that we are collecting with the patients in this framework, where we get data related to what are the devices that, first, what are the demographics, data about the patients, what are the clinical scores that the clinicians had determined that the patient had, and then depending on the device that the patient was using, for example, a shoulder and elbow robot or a wrist robot, we would then save the data of the training days and of the evaluation. And that would allow us to quickly in the future try to calculate the data. So here is the vision of the framework. We have the robot, we collect the data, we place the data in this framework that allow the person later on, the analyst, to calculate the metrics more efficiently. And the data is typically saved in this form where we have like, columns. We typically sample the data at 200 hertz, and what we have at each 5 milliseconds, we have the X and Y position in the case of the shoulder and elbow robot, as well as the velocity X, Y, and the forces that are interacting between the robot and the patient. Now, one of the things that is quite interesting is that robotic therapy doesn't help everybody. So, of course, it helps when we look to the studies and we look to the averages. We have very good and clear improvement. So let me just explain a little what you are seeing here. This was a study, a multi-site study that was published in the New England Journal of Medicine using our technology. And what you see here is that these black dots represent patients in receiving just usual care therapy. And you see how much they improve in one scale, one clinical scale called the Fugl-Meyer. Here you have the dates of the enrollment of the patient. So what you can see is that these black dots that represent the usual care are all pretty close or lower here to this to the zero, meaning no change, with a few of them actually getting worse and a few getting better. Then we have these blue dots that represent the robot therapy, and then you have these red dots that represent the intensive comparison therapy, when we try to get the therapist to deliver therapy at the same intensity as the robot one. And if we look to what is considered the minimum clinical important difference, very few patients of on the usual care actually improve more than what is considered the minimum that they need to change to improve quality of life. While you have several patients in the robot therapy and intensive comparison that do improve more. So while in average, we might say that robotics help, not everybody does benefit from the intervention. So the question that we have is what could we do to try to help the patient? So what I'm going to talk until the end of my presentation is how could we do to try to improve the outcomes. So one of the things that we did was to try to use something called transcranial direct current stimulation. You pass a very low current of 2 milliamps over the area that is where the stroke took place. And this is an anodal, which normally what means is that it tried to increase the motor evoke potential of the area that was affected. And then after we did this, we combine this neuromodulation with robotic training. But then what we want to know is, because we want to know if this neuromodulation would add value over the robotic therapy, what we did is that half of the patients actually did receive neuromodulation, but the other half receive a kind of a sham. We placed the electrode, but we didn't turn them on. So like the patient think that they are improving or think that they are receiving also the neuromodulation, but actually they are not. And then we compare the two groups. Now, what we saw when we looked to the clinical scores is that there was no difference. Now, the clinical scales, meaning that this type of technique didn't have an additional benefit to robotic training. Both groups improved quite a bit just receiving robotic training, and adding this to try to get patients to improve even further didn't make a difference. So the question was saying, well, the clinical scores are very coarse. They are not very sensitive. Could we learn something if we use the robotic metrics? Could we see something extra? So let's go to the next slide. So let me tell you a little about this study. So this study was done in two hospitals in New York area, and it enrolled 82 patients. So half of them received what I call the sham TDCS and then robotherapy, or they received the actual TDCS and robotherapy. So we evaluate the patient 3 times in a row to see that they were stable. And then we deliver 36 sessions of robotic therapy, either to the proximal shoulder and elbow or to the distal wrist, with, again, TDCS or sham delivered before training with the robot. After these 36 sessions, we evaluate the patient again, and then we waited 6 months, not only to see if they improve, but also if they were able to maintain the improvement after 6 months. So not only to look to acquisition, but also retention of the improvement. Here is the results looking to the clinical scores. So you have here patients at the admission. And then you have the pink one represent the robot sham. The blue one represent the robot and the TDCS. The black line is the average. So what you can see is that from admission, 36 sessions of training of therapy, patients improve with the robotic therapy, but there was no difference between the two groups. So actually, if we look to how many of them improve more than 5 points, that was the clinical improvement, we see that, again, there wasn't that much difference. Around maybe 70 to 75% in average improve more than those 5 points that I mentioned before. That means that they would have an impact in their lives. So that's pretty good. But there was no difference between the two groups, the sham and the TDCS group. They both improve roughly the same. And when we look to how not just the average, but we look to individual patients and how many of them improve more than 5 points, there was no difference between them. So now what we did is that we went and tried to look to the robotic metrics. And the robotic metrics is that we are asking patients to make movements with the robots. These robots are very back drivable. So you imagine that they are just like a joystick. During the evaluations, they are like just devices that would allow you to move freely. They are not constraining your movement. And during therapy, they might deliver forces to help you make the movements. So when we look to how the patients were doing, we can then calculate different things. We can, for example, see at the beginning when they were admitted, how many seconds it takes for them to complete one of the exercises. And then as time passes, as they train at discharge and follow up, we see how many seconds it takes them. The same, the deviation from the straight line. How straight are their movements? Humans normally try to make straight movements when they are reaching to objects. So we see how much they are making straight movements or not. We look to the speed. What was the mean speed, the peak speed? We look to other things like the smoothness of the movement and other aspects that typically we call we might be calling more micrometrics, that are aspects that we are looking into neuroscience with the concept that perhaps a continuous arm movement is actually a composition of discrete segments. So we look to what is called submovements. How many submovements are in each movement? What was the duration of these submovements? How they were overlap? So those are different aspects that we are calculating from the patient movement. And if that was with the shoulder and elbow, we do the same thing with the wrist robot. And we try then to see if perhaps we could see if we didn't see any difference either in the clinical scale or the robot metrics, maybe if we would try to see if there was a subgroup of patients that might benefit from the intervention, maybe we would prescribe, instead of saying all the patients would benefit, maybe we could just say that a small part of the patients in a particular characteristic would benefit from that. So we did a brute force approach to try to change the different windows that we would have different patients in and look to it. And again, we didn't see any difference. So that intervention, adding neuromodulation, at least for these patients, didn't make any difference. In fact, the only groups that show any particular improvement were a few small group of patients, but they were always benefiting the robot that had the sham therapy, the sham TDCS. So it wasn't like the neuromodulation was not adding any advantage. The other aspects that we did look is that in the same comment that I did before, that when we look to movements, this concept of segments that are blended together, When we look to the jerk is a measurement of smoothness. We see that as patients they start receiving therapy, what we see is that that metric goes down. It doesn't go up. They get worse. The movement becomes jerkier. And after a particular time, the movements start to get smoother. So it's almost as if you have movements where the patient try to make a movement, stop and see where their hands stop, and then make another attempt. And as they get better, they start to blend them. They start to blend these sub-movements, these attempts to make movements. They start to blend them. And as they are blending, in the beginning, this is worse than they are individual. But as time passes and they get much and more blended, they start to improve again in this marker. So that's an interesting marker because it's not monotonical. And what we did see, which was interesting, at least for people that are looking to rehabilitation, is that the same kind of behavior that we saw in the shoulder and elbow in subacute patients, meaning immediately after the stroke, after a few months, we start seeing the same pattern in the wrist data. So both of them, it almost looked that the distal is recovering, but recovering in a different time scale than the shoulder and elbow. So the shoulder and elbow recover faster, and then the more distal limb segments, but with the same pattern of recovery. So this was quite interesting, but now let's see if we could use, again, as before, this robotic assay as a biomarker. So like that, we just looking how the patient perform in the robots, we could estimate the clinical scales. And why this is beneficial is that first, depending on the therapist, there is a very large discrepancy in how they will score the same patient. We did a study many, many years ago showing that the kind of changes depending on the therapist that is performing the evaluation is around 15% of the total scale. So this is huge. So like depending on if you have multiple therapists evaluating patients, you would have a very big variation, not because of anything, but the fact that the therapists interpret the instructions slightly different. So we started like many years ago to look at the robotic metrics as a quantitative way to let us estimate the clinical scales. Here is an example of patients. So like you, of course, this is not clear for you, but this is a scale called the Fugl-Meyer scale. That perfect movement means 66 points. So this is a patient that at admission had a Fugl-Meyer of 9, and after the 36 sessions had a Fugl-Meyer of 16. That means it's a very severe patient. So when we ask this person to make movements to hit targets unassisted that are shown in a kind of a circle, a clock around it, the person cannot make the movements. They make a very clear attempt, but they cannot move and hit the targets. When we ask them to draw a circle, this is what they can do. They can like kind of move their shoulder from one side to the other. When we ask them to point with their wrist, they cannot do much of it. And then after training for 36 sessions, you start seeing here the person now being able to move and hit different targets. It's not a very straight movement. It's not a very smooth movement, but they are now able to go and hit all the targets. And they are able to draw something that looks like a circle, but not much more on the wrist. They still are not very good at the wrist. As I said, it looks that we are getting more first like the improvement on the shoulder and elbow before we get improvement in the distal limb segment. So this was a patient 9 to 16 in this scale. A patient 15 to 25 So from the onset, they can more or less hit the targets. Again, not very smooth movements, not straight. They can make something that look like a circle. They still cannot point well. But when they are 36 sessions later, they now can make movements that are far more straighter, something that looks much more clear circle. And they are starting to be able to move their wrist to point in different directions. So this was a patient 15 to 25. And just to remind you, perfect movement is 66 in this scale. And here is a patient 24 to 34. The movement, much like from the onset, able to hit everything, draw something that look like a circle, start to be able to point a little with their wrist. 36 sessions later, they are doing much better. They can hit all the targets. They can make something that look like a circle. And they are starting to be able to point in a pretty repeatable way with their wrist to the different targets that are presented. Again, this is essentially half of the scale. So a normal, again, is 66 points. So this is a person that is more or less at the very middle. So we applied the same concepts that we had before, that I showed initially, the nonlinear and linear methods, or using machine learning to try to estimate the clinical scores. And the first question was saying, should we use the shoulder and elbow robot data and the wrist robot data, or just one of them alone would be enough? And how well could we get when we compare the nonlinear models with the linear models? So we have to select features. So here we have all the different clinical scores are down here. And this is all the robotic metrics. So we look and try to see which ones have a correlation that are a little higher. Of course, when we look clinical scales with clinical scales, they are very strong. But then we start taking some of the robotic metrics that are somehow correlating better with the clinical scores for the shoulder and elbow and the wrist robot. Here are the specific ones that we selected. It's not perhaps too important, but it's just different metrics that we obtain from the patient making the movements, drawing circles, or trying to resist the movement. We then compare the linear and the non-linear. So here you have the R values. This is for the shoulder and elbow. This is for the wrist. When we use data from both robots, so we see that we can get R values that are quite well. So we can estimate this scale, this clinical scale, very well using the robotic metrics. And these are different other clinical scales, and some of them we do very well, others we are not doing so well, because this clinical scale still is not bad. The R values are of the order of 0.6 to 0.7, but this scale is very much dependent on the attitude of the patient. So a patient that is young and want to perform, they can score well in this scale, even though they cannot move much of their limb, because these are reflecting tasks that they need to do, and people can do the task with just one hand if they really want hard to do it, while these ones you're evaluating just the impaired side. Now, what we had shown is that we were able to estimate quite well the clinical scales using the robotic metrics. So we got R values that were quite high, but there wasn't like that much a difference when we combine both the shoulder and elbow and the wrist, suggesting that perhaps if we just have one of the robots available, we could just estimate this scale from that one, so then we can be a little faster in performing that. So In a sense, we had a very good correlation between the clinical scales for chronic scrot. The risk data was a very added value in terms of estimator, but again, of combining the wrist with the shoulder and elbow data was not very impactful. If available, we of course can combine, but if not, we should just take the data that we have to make these estimates. And this might be very helpful to get rid of the subjectivity that the clinicians would have when they are scoring patients. Now, what we are presently doing is trying to determine who is the responder and who is not the responder. Because if we could predict who is going to improve with the treatment, it would be very helpful because it would minimize the use of resources. So somebody that perhaps would not be improving much, maybe we should try to do something different, while the people that would be improving significantly, we should then try to maximize the time that they could get from this intervention. So we did use different styles to look at the data to try to predict the outcomes, either time dependent or time static techniques. And one that we did use is we looked to a very old conjecture from a German gentleman more than 100 years ago, Ebbinghaus, that what he called is forgetting curve. So he said that when somebody's training, the person would improve during the training. And then when they come back the next time, they don't come back and start where they left. They actually get a little worse and then they improve again. And this is a repeated process. So the concept of therapy is saying in a single therapy session, the person would be improving some of the metrics. When they come back, they didn't improve. They don't start where they left, but they improve again. And it's almost as if you have two time constants, a daily time constant and a long-term time constant. And the idea is that if we look to two sequential therapy sessions, we might be able to predict what is the outcome. And that could be very valuable in terms of predictors. So we use two different approaches, one the long LSTM, long short-term memory, and the other one was the multi-layer perceptron. And we did calculate for both of them, for the LSTM, for example, how many nodes and how well was the Matthew coefficient for the different combinations. So here we have the shoulder and elbow evaluation and therapy, the wrist evaluation and therapy, and here is the clinical score. So here we are taking everything. And then here we are trying to just take the data from the wrist or just the therapy data, not the evaluation. So we can see how to get the best possible result. So at the end, we have an idea of what would lead us to the best outcome. And the same thing if we look to the multi-layer perceptron. Now, this is still preliminary. This is actually, we are just going to be finishing now this paper. We were a little surprised that the LSTM model did not outperform the multi-layer perceptron, and we are trying to understand what was the data, what was the reason for that, because we did expect the LSTM to do better. But it seems that we'll be able to estimate who is a responder and who is not a responder from a particular intervention just by looking to two sequential therapy days. Now, in conclusion, this neuromodulation that we deliver, nodal TDCS, did not add in terms of final outcomes beyond what robotic therapy was able to perform. If anything, we saw that patients that did not receive, that were sham TDCS, improve a little more. But they all improve dramatically. If we look the total, they all improve more than 70% of the patients improve more than the minimum clinically important difference. So the robotic therapy has a very clear benefit. And we also can see that if we use machine learning, we can estimate very nice biomarkers that have a very high correlation between the kinematics and kinetics and the clinical scales. The non-linear models were better than the linear ones. And there is early evidence that if we get 2 sequential therapy sessions, plus the admission, the clinical scale at admission, it seems that we can estimate quite well who is a responder and who is not a responder, which would allow us to allocate resources more carefully and point the non-responders to perhaps alternative forms of therapy. So with that, I'm going to stop here. And I appreciate your patience and attention. So let me stop sharing and take some questions. Thank you.
Thank you, Professor, for your wonderful session.
No, thank you.
Dear students, if you have any more questions, please raise your hand. We will enable your mic.
Good morning, Professor. This is Tamil Shelvi from EC. So
Good
you have
morning.
yes, sir. So you have explained about that this biomarker, sir. This I'm having one doubt. You make use of that MLP layers for learning that network, but whether this deep learning CNN is possible in this, sir?
So it could be. I don't see why not. We just selected these two because was the two approaches that we felt would be more appropriate. But it's possible that CNN would also help you like understand some things. So as a parallel, let me tell you something else we are presently doing. So presently we are using the cell phone to have the family members make a video of the patient. And then after we collect the data with the video, we then try to estimate what is the clinical score of the patients. In that case, we are using CNN. We are trying to see if we can use CNN to help us identify different features and then try to again estimate the clinical score. But in this particular study, we did not use CNN. In the one that I'm talking using the cell phones, which is ongoing, we are using CNN. I don't know yet if it will be, I don't know the results yet.
Okay, sir. Thank you, Professor.
You're welcome.
Good morning, sir.
Morning.
Sir, I have one doubt. What are the important quantities are used in kinematic analysis?
So let's see if I understand your question. You are saying what are the important quantities? So when we are making different movements, let's say an unimpaired person making certain movements, there are very clear kind of characteristics of behavior of healthy movements towards, for example, objects. And so what we try to do is to look to the same kind of movements that patients would be doing, and then trying to see how far these movements are from the movement of a healthy person. So for example, if you are reaching to a target, you are making pretty much a straight movement. There is no reason for you to do this, but we humans like to make straight movements. So when we look to the patient and we say hit a particular target, that's all that we are telling them. We try to see how straight was their movement, and then we look to the deviation from that straight movement, because that's what the healthy person normally would do. And then we use this as one of the biomarkers. Now, because the precision of the robots, we can have a much better accuracy or effect size when we are calculating different aspects of how the patients, at what stage the patient are. So I'm not sure that I answer your question, but this is like what we are trying to do with this robotic metrics.
Okay, sir. Thank you, sir.
Thank you.
Professor, are there any definite way to decide how many features are needed to get a better output? Probably depending on the input data size or something.
So what we did is that we start looking, we kept increasing the number of features to decide how many features would be required until we more or less achieve a plateau. So this was very empirical, and we more or less got around 8 features. We had, I think, if my memory is correct, 34, 36 features, and we just kept like, using all the features, taking one out and keep seeing it until we saw what was the minimum kind of number that we have, that the correlation kind of plateau and didn't improve further. So that was empirical, how we determine how many features.
Okay, thank you.
You're welcome.
Any more questions? I'm also.
Good morning, sir. Sir, I have one question, sir. Sir, how kinematics is used in everyday life, sir, in your point of view?
I could not understand what
Sir,
you asked. I'm sorry.
Okay, sir. Sir, how kinematics is used in everyday life, sir, day to life?
Somehow the connection is not very good, and I still can't understand you. Sorry. Would you like to try again, and I'll be trying to understand your question?
Sir, how kinematics is used in everyday life, sir, or day-to-day life? We have to use.
So if I understood your question, you are asking how is the kinematics that is normally used in day-to-day life? Is that correct?
Yes, sir. Yes, sir.
Okay. So the basic, when we look to kinematics that humans are doing when you are making straight line movements, and you look in the neuroscience literature, there are some features that are kind of common that healthy subjects would have. So for example, we try to maximize smoothness. So we are trying to make the movement, say, from this point to that point, might be a straight line, but we also are trying to make the movement as smooth as possible. So then you can go and look to things like the metric that I mentioned, jerk, that is the derivative of the acceleration. So you have the position, you have the velocity, you have the acceleration, and then you have the jerk. So the jerk can be used to determine how smooth is the movement. And we see that humans like movements that are smooth. So we are like, taking advantage of what I'm not a neuroscientist, but we try to take advantage of what neuroscience had educated us in terms of behavior of movements that healthy subjects would perform. And we use this to try to be kind of the goal that the patient, that will compare the movement of the patient to. I hope I answered somehow your question.
Yes, sir, I understood, sir. Thank you, sir.
Thank you. So I'm not sure if anybody else has a question. If not, I'm going to say goodbye. And again, thanks the organizer for inviting me. It's a kind of fun to have this opportunity, even though sometimes these new ways of communicating might not work as well, but it's always like a pleasure to have the opportunity, and I thank you for inviting me.
Thank you, sir, for your valuable and informative speech, sir.
So I'm going to
Thank you, bro.
thank you.
Thank you.
Be well.